I want to welcome everyone to this, the very first webinar of the Australian Nuclear Association. I'm John Harries, Secretary of the ANA, and very pleased to welcome you all. You see on the screen there is a question and answer, so that there's a question and answer area for which you put a question in, which will go to Mark and he'll be able to answer it with hopefully or with assistance. A video of the webinar should be available after we've finished this event, and also the slides will be available. There'll be a link on the ANA website. The topic of this webinar is an update on nuclear power, new builds and research and development. The speaker is Dr. Mark Ho. Mark is President of the Australian Nuclear Association and works at ANSTO as a reactor heat transfer specialist. His research interests include reactor design and deployment. He currently supervises 3 PhD students studying reactor development and safety analysis. Here's Mark.
Yep, welcome everyone. Thanks for coming to this afternoon talk. I will try to keep everything very concise and interesting, so let's head straight into it. So I'd just like to talk about just what are the grand numbers. At the moment, nuclear power provides about 10% of the world's electricity. There's 441 operational reactors according to the IAEA, and providing about 2,500 terawatt hours in the year of 2018. And if you look at the global fleet in terms of nuclear power, we have different varieties of nuclear power plants. So we have pressurized water reactors, pressurized heavy water reactors, which is Canadian technology. We have light water cooled but graphite moderated reactors that are only operating in Russia at the moment. We also have about 14 gas cooled reactors, which are the UK indigenous technologies that are still going for a couple of years yet. And then there's 2 fast breeder reactors, which are basically sodium fast reactors operating in Russia, and boiling water reactors as well. So operating in the US as well as say in Japan. But you could see that most of the global fleet in nuclear power is actually with pressurized water reactors. And it looks to be, this trend looks to be about the same with our new constructions as well. So in total, there's about 54 reactors under constructions according to other IAEA. And most of these 44 units are PWRs. There are also some heavy water reactors under construction. These are all in India. We've got 1 unit of high temperature gas reactor under commissioning over in China. 1 fast breeder reactor, the sodium fast reactor, under construction in India, and 4 boiling water reactors under construction still over in Japan. But you could see, you know, this is the picture. Dominant is pressurized water reactors still of the 1 gigawatt variety. So, I mean, for those of the audience that aren't familiar with pressurized water reactor technology, I'm just going to quickly go through this. So what's pressurized water reactors? Some like to call it a kind of like a glorified kettle, but boiling water at a high temperature and high pressure. So what's known in the pressurized water reactors, it's composed of a primary loop, from which you take the heat generator away from the core. That heat is donated into a secondary loop, generating steam at say 70 atmospheres of pressure, and that turns the steam turbine. And the primary loop coolant recirculates back, gets pumped through, and then back into the core where the water cools the reactor. But what's important to note is that the water has another quality to it, which is to slow down neutrons. The neutrons hit the hydrogen atoms, they're very efficiently slowed down, and that makes the neutrons easier to be absorbed by the uranium fuel that results in the fission. And then of course you've got your control rods, which could be inserted in the core and absorbs the neutrons to kill the nuclear reaction if you want to shut the reactor down. And of course, completely surrounding all this is the containment vessel, so that in case there might be an accident, then the fission products and the radioactivity is contained within that structure. So these pressurized water reactors have become the dominant nuclear power producing units around the world, with 298 units worldwide. And to give you an idea of the scale of the engineering, I've just got a few pictures here. Here, what you're seeing is part of the RPV, or the reactor pressure vessel, which is currently in the furnace somewhere in Russia, being forged in this picture here. So it gets heated up and it gets forged, and you can see the scale of the construction and just the kind of heavy industry required and the kind of robustness in your supply chain required to have a very strong nuclear industry. And these forges will only exist in a couple of places around the world. So, for example, in China, in Japan, over in South Korea, all these countries which have had a very, very continuous nuclear power build for the last 30 years will have these type of kit and these kind of machinery. And in this picture, you can see that the two parts of the reactor pressure vessel being brought together and being welded. And if you look at the detail around where it's being welded at the moment, you can see it's, the area is actually getting inductively heated to 300 degrees before it gets welded together. So all this is very, very specialized knowledge, very, very particular and bespoke technology that's been developed over a long time. So the Russians are very dominant and also very mature in handling and in researching and deploying reactor technology. And this is also shown in the recent commissioning of their floating nuclear power plant. This, what's known as the academic Lomonosov, which is the KLT-40S small modular reactor, one can say, 35 megawatts each. This barge has two of these units producing 70 megawatts. And this has been currently in deployment in a town called Pevek, which is a gold mining town within the Arctic Circle in the northern Russia. And so now looking at the numbers provided by the IAEA, and this is the list of what the IAEA regards as reactors under construction, you can see the strength of the Russian nuclear exports. It's currently got 2 units under construction over in Bangladesh, in Belarus, and also within Russia itself, 4 units. And you can see they're pretty much all VVERs, pressurized water reactors, as in the Russian acronym, and they output gross 1,200 megawatts. And then further on, Iran is building 1 unit VVER, and then Turkey as well, another VVER of about a gigawatt. And then there are some kind of legacy projects which never found completion, such as the smaller unit over in Slovakia and 2 units of VVERs over in Ukraine. So moving on, another major nuclear builder is China. So here is a bird's eye view of the Hualong 1 reactor under construction. You can see the reactor containment building, the top of which is being lifted in place by the heavy lifter. And the Chinese have embarked on a very thorough and methodical rollout of their pressurized water reactor technology. So here, what's listed is what's currently under construction. And you can see that for those of you noticing the construction start dates on the left, a lot of them starts in the year 2015, and that's just for good reason, because the manner in which nuclear builds go ahead in China is actually usually within 5-year plans, because these are state projects, and so a lot of the construction start dates are actually for the period of 2015, 2019, 2020, and so the numbers shown here, apart from these 2 constructions of the Hualong 1 HPR 1000, there's actually a lot more constructions to come. And to give you an idea of how quickly this rollout has been, the Chinese have increased their nuclear capacity from 27 gigawatts to 54 gigawatts in the space of 5 years. And the lower estimate of the nuclear power rollout is to have 130 gigawatts by 2030. And then noticing as well, you can see that some of these projects are of CNP 1000 and ACPR 1000 designs. And these are the two models which are the mainstay of two separate state construction entities for nuclear power builds. So China National Nuclear Corporation and China General Nuclear Power Corporation, they have had separate reactor, pressurized water reactor models, but they've actually been instructed by the state to work together to come up with a standardized PWR of a 1 gigawatt capacity. And the result of that is what's known as the Hualong 1 or the HTR 1000. So you can see the other new constructions, they're all Hualong 1 in Fuqing, in Fanchenggang, and then these other locations as well. And even in the export of nuclear exports over in Pakistan, even though these units are specified by the IAEA as ACP-1000s, if you look at some of the more recent reports, it's very possible that these are basically going to be Hualong 1 units as well. For those of you amongst the audience who are very eagle-eyed with detail, this small unit here, this 200 megawatt unit, which is the HTRPM, stands for High Temperature Reactor Pebble Module. And this is actually a prototype high temperature gas reactor, which is currently under commission, and it was sort of expected to have finished commissioning last year, but it's probably going to be happening this year, late this year. And I will be talking about that a little bit further on. So crossing over the Pacific, the US have their own Generation 3 plus pressurized water reactor, which is known as the Westinghouse AP-1000. Here is a very recent picture of the construction of that reactor over in Georgia. So what's known as the head vessel, which is a large water reservoir sitting directly on top of the reactor building, has just been put in place. And the AP-1000s really was the US response to having the nuclear renaissance and having a second wave of PWRs deployed. Although because the US, as well as I guess in Europe, they haven't been building many PWRs or large 1 gigawatt reactors, their supply chains has to kind of get back into shape. And so that's why we've been seeing delays and somewhat cost overruns. However, the US are committed to seeing through these two projects, and they will be commissioned within 2-3 years' time. So we have 2 units underway, under construction over in Georgia at the Vogel sites. And in terms of the Americans, North American and South American continent, in Argentina, they are also building a very small modular reactor known as CAREM. So I think that reactor pressure vessel has been installed and constructing the containment building around it. So moving on, very important to note, South Korea and Japan. So Japan, traditionally a very large nuclear power user, actually still have some boiling water reactor projects on the way. So these 2 units down on the bottom, of course, after the Fukushima accident, everything was put to a stop because all these projects required review, and so that's contributed to the delays. Whereas in South Korea, they are currently constructing or finishing construction of the APR 1400s, which is the mainstay, the Generation 3 reactor, and also the very, very successful build out over in the UAE, of which all of these 4 units are currently coming, these projects coming to a completion. So what's not often talked about is also India, because we hear a lot about the AP-1000s and the European pressurized water reactor. But if you look at India, India also has plans for nuclear power. So, and what's interesting as well, they're not just building PWRs, they're building a combination of heavy water reactors, which uses heavy water or deuterium dioxide for cooling and moderation. And also they have a fast breeder reactor or sodium fast reactor currently still under construction, as well as the fact that they've got some Russian projects, so 2 VVERs under construction. And what's possible is that I think the US Trump administration signed an MOU with India to possibly export 6 AP-1000s as well, but those projects aren't recorded on the IAEA website yet. So the reason why they have both pressurized heavy water reactors as well as fast breeder reactors is because India has something known as what's known as 3 reactors program. So they want to use the heavy water reactors to breed plutonium for fuel to be used in the sodium fast reactor, and then to use the neutrons or the excess neutrons in those sodium fast reactors to breed uranium-233, which is basically to develop the thorium fuel cycle. Because if you expose thorium to neutrons, you will get uranium-233, because it captures a neutron, transmutates to protactinium, and then further capture transmutates to uranium-233 with a beta decay becomes uranium-233, and then they can extract that with fuel processing and to reburn that uranium-233 fuel inside another advanced heavy water reactor. So this is actually India's kind of like grand strategy of how to fully utilize their thorium reserves. So that's what I think is very interesting. So also, not to be forgotten is France. So AREVA, or Framatome, as known now, has the European pressurized water reactor project. Here is actually the unit over in Finland, over in Olkiluoto, unit number 3. And France currently has 4 units under construction or underway. So Olkiluoto is at the point where it's looking at hot commissioning, so it's nearly coming in at close, that project. The Flamanville project within France itself is also under construction. And of course, over in UK, 2 units are under construction over at Hinkley Point C. And basically, the interesting thing to note, of course, is that Framatome is basically underwriting the risk of this UK project, because the UK government has negotiated with AREVA and agreeing to pay AREVA basically a price of £92.5 per megawatt hour of electricity generated. Is quite a high cost in terms of electricity, but actually the UK government doesn't bear the risk of this particular project coming into cost overruns or schedule delays. So that's an interesting way of financing this project. And also over in Brazil, there's another reactor. It's a very older reactor, which is actually of a German design, which used to be KWU Germany, is now a Siemens entity, and that reactor has yet to be completed as well. So with the challenges facing the West, I would say, in terms of large reactor construction, what's very interesting to note is that the US, I think, has responded by innovating. And so there's a lot of activity and a lot of discussion about the prospect of small modular reactors. So for those of you who aren't familiar, what small modular reactors, it's generally known as a reactor which only outputs 300 megawatts or less instead of 1,000 megawatts. And the reason behind this miniaturization is really so that you can get a very, very large reactor unit kind of miniaturized so it can be completely fabricated inside a controlled setting, inside a factory environment, so that the quality of your units can go up and then the cost of those units could go down as well. Kind of like similar in the manner in which large fleets of aircraft are constructed in a factory. And so you can see, as an example, you have the standard kind of like subsystems that combine is your reactor. You've got your pressurizer, steam generator, coolant pumps, and reactor pressure vessel. And you can see how all those separate systems could be combined inside this one module. And so the whole module can be prefabricated and then transported on site and deployed so that you can reduce those large reactor construction times from something like 8 to 10 years to something like, say, maybe 3 to 5 years. And so in terms of a price tag, it's important to note that what the US in this particular instance, NuScale, is calling for is to aim for a price tag of 12 of these units deployed inside one plant, and the overall flat price tag of a combined 720 megawatt plant will be first of a kind price, $3 billion US dollars. And this normalizes to about $4.16 million per megawatt of capacity. And this is a kind of like a figure or a price tag that's approaching what would be deemed as being a competitive price compared to, say, a Russian or a Chinese design. And of course, more importantly, is that if you can construct these units within a shorter time frame, then you can also have these plants generate electricity and making a return on your investment quicker than you could for a very large build. And this is actually the actual size relative to a large gigawatt reactor plant. Of course, when we're talking about new technology, there's also a strong onus on safety, because as much as we know that Generation 2 reactors are operating safely around the world, safety is part and parcel with good design. And so if you could design something which have what's known as passive safety, meaning that if you could, say, have a large water reservoir and having that water reservoir in place so that it could be called upon to take away the decay heat after these reactors are shut down, then you can also reduce the amount of complexity in your system, so you can further reduce the cost of that system. And in this particular example for NuScale, there's enough water so that it could basically be what's known as walk-away safe, because after a long period of time, the decay heat reduces to such an extent that just natural circulation of air is enough to remove the decay heat after the reactor's been shut down. And of course, you know, the reason for doing this is so that in case you have a station blackout event, as there was over in Fukushima, then you don't actually have to worry, because you've got all that cooling capacity there to remove that decay heat, and you won't have any meltdown. So those were basically a kind of an overall look at PWR technology and small modular reactors of the near term. So now I'm just going to talk a little about the advanced design. So the high temperature gas reactors, molten salt reactors, and the sodium fast reactors. So I think one of the most exciting projects on the way is the high temperature reactor that's under construction in China. So this technology is very different from pressurized water reactors because the fuel itself is very different. So you can see in this graphic here, the core is actually composed of these what's known as pebble fuel. So these are kind of like tennis-sized balls of pyrolytic carbon silicide composite. And there's these very, very small kernels, uranium dioxide pellets, thousands of them inside these balls. And the idea is that the graphite moderates or slows down the neutrons, but also serves to act as a thermal heat sink. So if you shut your reactor down, then the heat is absorbed by that graphite ball, and it's actually very, very resistant to damage at high temperatures. So these types of fuel has been proven and tested to not melt up to 1700 degrees C. And for these systems, they are not cooled by water, they're cooled by helium instead. The moderator, as I said, is made of graphite, neutron shielding is just concrete, and they use trisol fuel, or the pebble-based fuel. Operational characteristics is that they operate between 250 to 750 degrees C. The helium pressure is at 70 atmospheres, turning heat's donated to a secondary loop, turning a supercritical steam turbine at 40% efficiency. Reactor lifetime is 40 years. So the Chinese are commissioning the prototype now. And as I mentioned, the prototype unit actually has two separate reactor pressure vessels feeding heat into one heat exchanger, which gets delivered to a turbine. So that's the prototype, but what the Chinese want to do in the future is actually have 6 units surrounding one heat exchanger, and for all 6 reactor pressure vessels feeding heat into one heat exchanger and outputting 600 megawatts. And the reason why the Chinese are interested in doing this is because they want to deploy these reactors inland so that it can be air cooled. It doesn't actually require liquid cooling, because if you have a temperature that's of a reactor of high enough temperature, you can actually use direct air cooling to cool your secondary loop. So this would be very good for deployment for arid regions. So the US is also looking at advanced reactors as well, so not wanting to be left behind. There's been a recent announcement by the US Department of Energy to undertake what's known as the Advanced Reactor Demonstration Program. So this, in the fiscal year of 2020, is going to be slated $230 million worth of investment. And one of the prerogatives is actually to have an advanced reactor built and switched on within 7 years. So this is extremely ambitious. And they are looking at building 2 advanced reactors, and I would say that 2 leading designs under consideration would be a high temperature gas reactor known as the XE100 from X Energy that outputs 100 megawatts, and a very different molten salt reactor, which actually is of a Canadian design, this terrestrial energy 100 megawatt electric unit. And so they want, the DOE basically wants a reinvigoration of nuclear reactor research in the US, not only in PWRs, but also looking at the reactors in the future. And it's set up this $230 million fund so that it could have a cost sharing arrangement with commercial and the government entity. So another very important technology that they're looking into is additive manufacturing. So what you're seeing here are actually examples of silicon carbide structures which have been sintered into these very, very complex geometries. Previously, structures which couldn't be manufactured easily if we were to fabricate them as plate and then weld it together. So top left is actually, I think, an example of prismatic core being 3D printed by BWXT, and over down in the bottom right are examples of Oak Ridge 3D printed structures. So by being able to print your core using silicon carbide and then placing, for example, trisol fuel, which is these little uranium dioxide kernel fuels, for instance, inside the structure, you can have a very, very well controlled and fabricated structure. But more importantly, there's an onus and a focus on making sure that they are taking in data as they're manufacturing this, so that they could spot whether there's any fabrication defects as they're making it. And in that way, it would make it more easily to qualify those structures for reactor operations. So some of the other designs I'd like to just briefly talk about. So the molten salt reactors that I talked about previously with terrestrial energy, they are really kind of like an extension of the US molten salt reactor technology back in the 60s, using a thermal spectrum of neutrons, meaning neutrons would just slow down after colliding with the light elements within the FLiBe salt, the fluoride lithium beryllium salt. There's a different design of molten salt reactors, which are known as fast spectrum or molten salt reactors. So one of these designs under study by TerraPower, which is famously financed by Bill Gates, is to use a molten chloride fast reactor, a chloride-based salt, instead of a fluoride-based salt, because with a faster spectrum, you can actually burn depleted uranium, you can burn spent fuel, you can burn minor actinides, and the business case around the TerraPower molten chloride fast reactor is actually to utilize the accumulated spent fuel inventory in the US. So I think that's a very interesting project, and it's not only TerraPower that's pursuing this, also pursuing this is Elysium Industries, for instance. And then back looking at mass deployment of again, a more conventional molten salt reactor of fluoride salt is the Thorcon reactor. And the idea of these reactors is that they will be built in shipyards and deployed in island nations, for instance. So this is known as like a floating nuclear power plant, molten salt reactor. And the goal of this type of design is to reduce the price of electricity to 3 cents per kilowatt hour. So we will see. Of course, I will leave the discussion about the licensing of these reactors later. So sodium fast reactors are very important to note because they're known as the physicist reactor. Physicists usually love these reactors because the sodium coolant gives you the best neutron efficiency because it doesn't absorb neutrons very easily. And so when you have a reactor with lots and lots of neutrons, excess amounts of neutrons, you have options. What you can do is you can use those excess neutrons to either burn radioactive waste or to, say, annihilate weapons-grade uranium, as the BN600 has been doing in Russia for the last decade or two. Or you can breed fuel. So, you know, you can expose a blanket of thorium to produce uranium-233, or you can expose a blanket of uranium-238 to produce plutonium. And the details of this reactor, this BN800, for example, the second unit operating over at Belyarsk, it's actually quite complex because, you know, it uses sodium, so sodium is chemically reactive, so you actually have to design systems which make sure that any kind of spillage can be contained and won't result in chemical explosions or fire. And so this system uses 3 instead of 2 cooling circuits. And of course, being sodium, the operation temperature is a little bit higher, so you get various improvements in efficiency. So this fast reactor technology or fast neutron reactor technology is quite thoroughly studied in Russia. And for the BN800, one of the tasks or one of the missions of this reactor is also to look at the next generation of fuel forms. So the uranium dioxide fuel pellets, for instance, has been with us for a long time. In the future, the Russians might use this unit as a test bed to irradiate carbide-based fuels or silicon carbide fuels. And so this is a work in development as well. So a very exciting development, not so much on Earth, but out in space, because as you might know, the US is getting back into commercial, getting back into having a presence on the moon, having a permanent presence on perhaps maybe Mars in the future. And for that, you need a robust supply of power. And what better way of delivering that but in the nuclear form? So one of these designs that's actually been tested over at Los Alamos is something known as the kilowatts power reactor. And the design of this is very different from a conventional reactor. So the schematic you see on the left here, the reactor core is actually just a solid billet of highly enriched uranium, alloyed with, say, about 7% moly, and the structure is surrounded by a graphite reflector, it's beryllium dioxide, and to take the heat away from the core, it uses something known as heat pipes, the kind of passive heat removal technology that takes the heat away from the graphics chips of your computers. Actually, heat pipe technology was originally invented in the US nuclear lab, and it found its way into the IT industry, and now it's kind of finding its way back into advanced reactor construction. But the Americans, they tested this unit and they know it works. And so the next step, of course, is to look at deploying them in larger units. But what's also very interesting is that the spin-off from this is that you could re-engineer this in the package so that you have what's known as microreactors deployed. So what you see here is kind of a prismatic core having heat pipes, taking heat away from that maybe 3D printed core and outputting electrical power of 1 megawatt. So the heat taken out of this core would be delivered to a heat exchanger, which may turn, say, a Brayton cycled supercritical CO2 turbine, and the deployment of these units is either for remote regions or for military bases, which are rather remote. So I think there are a lot of interesting technologies to remain observant of, and as the audience might know, there has been a recent investment roadmap discussion paper released, and it does highlight nuclear technologies as something which we should keep an eye on. And I think, Australia, with its own National Nuclear Laboratory, with its own Opal research reactor, Australia has a working knowledge of nuclear reactors, and it serves as a great basis to remain informed because we have many specialist teams in ANSTO to give a thorough appraisal of these technologies. But having said that, the presentation I just gave is really a rundown of my own point of view representing the ANA, and I'm not really speaking on behalf of the government or behalf of ANSTO. So thanks very much for your attention.
Well, I guess the question now is, are there any questions that people have got for Mark? You can either, if you have a question, you need to put a mark in the question and answer part of the thing, and then I can either switch you on or I can ask the question itself. So has anyone got any questions to Mark? Chris Skinner has asked the question, Mark, thanks for the stimulating and informative presentation. What about nuclear propulsion reactors?
Well,
space reactors. So is that a good way of going into space?
Oh, well, I mean, well, most nuclear power, most nuclear reactors which power submarines and aircraft carriers are of the pressurized water reactor variety. So, for example, somewhat similar, I guess, to the KLT-40S units you saw that I presented earlier. Those are quite heavy. So to deploy them into space, everything is about minimizing the weight. And so this is why the reactor that you saw later on with the kilopower reactor, that's a much more miniaturized and a much smaller version of a nuclear package compared to those PWRs. So I would say, like, not necessarily, not really.
Ian Hall-Lacey asks, any comments on the Holos microreactor?
A Holos microreactor? I'm not sure if I know of this reactor. Maybe you can...
I'll see if I can get Mark to allow Ian to talk. Oops, where are you on to? Now, Ian, are you there?
You have to unmute him, or he has to unmute himself.
Yeah, there's been a bit of commentary on it recently. Goes up to about 10 megawatts, but it has some very interesting developments. It's sort of four cores which are brought together to be critical, and each core is subcritical. And that's the control of it, which is interesting, and also the turbine is linked lengthwise to it and magnetically suspended. but it's basically being designed with the US military, but with some civilian applications in mind. I think Holos-Gen is the website, and there's quite a bit of information there, but not as much as I'd like.
Thanks, Ian. You got any comments, Mark?
Yeah, well, thanks for notifying me about this particular reactor. I haven't heard anything about it. There are actually many microreactor designs floating around, which I didn't have time to cover in the presentation. So, for example, one of those designs is the Oklo Aurora design, which is just kind of like a startup company. It's finding a lot of support from the DOE, and it could become one of the demonstration reactors down the track. And those, I mean, a lot of these reactor technologies utilize a lot of technology that's been developed back in the 60s and 70s, and it's just kind of found its way back into application. But yeah, there's lots of development. That's all I can say, and it's hard to keep track of all of them.
All right, moving on a bit. John Tillerman, are you there? Do you want to ask this question?
Unmute now. Yes. Okay. Are you hearing me?
Yes.
Yes, we are.
Yeah. Well, look. Thanks, Mark, for your talk. My question was about Russian technology.
Yes.
And you did cover quite a bit. My thought is that the one interesting development in our part of the world is basically the move into Bangladesh. The two new units there, the Ropur, I think it's called.
Yes.
And the model that the Russians are using there is the term right, all in and all out. I think we had something like that way back in Australia's early history, that there might be all in, all out nuclear technology.
Sorry, what do you exactly mean by all in?
Oh,
all out?
you provide the facility.
Oh, right. Yes.
You provide the fuel, and then you take the spent fuel away.
Yes, I mean that's a very Russian trait, I think. I mean,
yeah, and a very valuable one, though.
Well, yes, very much so. I mean, the conditions, I think, it's very good what the Russians offer, because, for instance, I mean, I've read the article that the Russians in the negotiation with any country, they can offer exceedingly low interest rates for their finance, right? I mean, for instance, I think in the project that's looking to get underway over in Egypt, we're looking at, say, 3% finance, which is a lot cheaper than some of the commercial projects underway over in the US, which might be 7 or 10% finance, for instance. And the Russians, in some ways, uses, I think, the export of reactor technology is somewhat of a soft power, because if we have such a large investment and you have long-term fuel contracts, it really builds on the relationship between these two countries. And these reactors, they could possibly operate from 60, 80, even 100 years. Then you could have a very well-established relationship with any country that Russia is exporting to. So,
all right, thanks for that. Adam, I've lost Adam. Where's Adam? Adam Corey, are you able to unmute?
I think so.
Can you ask your question to Mark?
Certainly. You mentioned the Indian model of the 3 reactors.
Yes.
What are your opinions on the success for extracting all the potential energy from the fuel, as well as reducing the amount of waste produced? And is this a feasible model that other nuclear using countries could adapt?
That's a great question. And I would say, first of all, we have to understand a little bit of the context of which India runs by. So India has really, for a long time, kind of been out in the wilderness, because it's obviously has its own weapons program. And so it's actually in contravention of the non-proliferation treaty. And so for this reason, there hasn't been much technology exchange into India, and they've kind of had to develop the technology indigenously for a long time. But now we're actually seeing a softening of attitude towards that. So, for example, as I mentioned, AP-1000 reactors are looking to be exported to India. And so when the Indians are investing in thorium fuel cycle, it's not so much really on the basis that, yes, they can severely reduce the amount of nuclear waste, because obviously whenever you have to have any reprocessing, there's other waste streams being generated, you see. And so the Indians, and I guess along with the Chinese, because they're also looking at the thorium fuel cycle, are really looking at the thorium fuel cycle more from an energy sustainability and an energy security perspective, so that they don't have to really be necessarily reliant on uranium imports, for instance.
Yeah, all right, Mark, we got an anonymous question from, hypothetically speaking, looking in your crystal ball, just say the Australian government policy change and decided to pursue nuclear power. If you had to back a technology to be Australia's first nuclear power reactor, which design would you back?
Oh, wow, that's a very personal question. But look, I think that's a great question. And I think, for Australia, the social challenges is even greater than the technological challenges, right? I mean, I'm here, I'm sitting in front of you, I can talk about the technology. For nuclear professions, we have a thorough understanding of technology. It's just hard to communicate that. And so therefore, even though we might not necessarily need the best in terms of a reactor design, in terms of having intrinsic safety or passive safety, it's a good idea to get those type of designs into your country, because sometimes coming second is better than coming first, because we get the better technology, right? And I'd say, for Australia, a near-term deployment would be something like a small modular reactor. I would say probably maybe of a NuScale variety, not for any particular reason that it might be superior to another small modular reactor technology, but for the fact that, they're so far down the line in the development, and that they've already plowed in, close to $1 billion on investment just to get the license, just to get the design to a very, very detailed design, and also to have that reviewed and going through the review process and getting the design license from the NRC, for instance. So Australia can really capitalize on the investment that's already been made overseas, and so that we can be confident that we can deploy this technology successfully after it's been demonstrated, say, overseas in the US. But I say this, but I don't actually rule out anything. I think that more and more there's been lots and lots of positive stories about the advanced reactor designs. There's been lots of investment. So, we're in Australia, we're somewhat in our own little bubble, and we don't hear a lot about all the activity at work, for example, over in Canada National Lab, where they want to have the fourth generation of reactors, or the non-water-based small modular reactor developments to be done over there. So I think that there's lots of opportunities, and we should keep all our options open.
What about the BWRX 300? The thought process of having a boiling water reactor, SMR.
I think that's a very real design as well. So to put the BWRX is a serious design that
you might just explain really, what it is.
Yeah, so it's a boiling water reactor, 300 megawatts as well. And the idea of this is that the details of this is to severely reduce the amount of systems, even compared to, say, a NuScale design. And so they're quoting maybe a unit price, maybe half that, per megawatt of capacity delivered. And the focus, as I understand it, is really to reduce the amount of nuclear grade concrete or high quality concrete required to construct these units. Though I would say that, in terms of the design, it's not as far along in terms of its developmental timeline as NuScale. And so, I would, be very, very interested and also very mindful and observant of any development in that area. But I would say that, you know, GE, General Electric, has teams and teams of scientists and engineers working on the design. It's an evolution from the, you know, their advanced boiling water reactor technology, a design which has already been licensed in the NRC. So I know it's a very, very real design. It's not just a paper reactor, but of course, you know, that's just not as far down the line of development as the NuScale design.
Thanks for that. Now, I think probably the last question probably now. We've got another one from Ian Hall-Lacey. I don't know whether you're here, Ian. Are you want to answer that question?
Mark, after decades of quietness, if not going to sleep, the US has suddenly burst forth with an enormous variety of small reactor innovation in the last 15 years or so. Can you make some comment on that relative to other countries and Europe and China and Russia, for instance?
Well, I just think that, you know, it's a combination of happy coincidence. So I think the current Trump administration is very, very supportive of nuclear power, for instance. It's also, it knows that, you know, nuclear technology has come into, its day is coming as well because of advances in, say, you know, as I mentioned, advanced manufacturing. And I think also in the end, you know, the Americans really don't want to give up that easily its predominance in nuclear technology, because still currently, even though the average reactor lifespan, I mean, lifetime of a reactor over in the US is about 38 years from memory, it's still got the largest PWR fleet in the world, right? So I think, you know, despite the low price in gas in the US, it wants to regain some lead in the nuclear engineering realm. And I think the way to do that for the US is to innovate. And so that's what I think, you know, why they're thinking about it and actually doing something about it and investing into it.
We might have one more question. I think Chris Skinner had a question. Are you there, Chris?
Which of the various designs that you've given us an insight to would minimize the long-term quantities of radioactive waste?
Well, actually, a lot of the Generation 3 reactors are designed to maximize fuel burn-up, what's known as fuel burn-up. So for instance, you know, the EPR, from memory, uses 17% less uranium dioxide compared to its previous N4 design, which is another PWR design of AREVA. And so, you know, the measures in, you know, nuclear parley is that your burn-up, your fuel burn-up or fuel utilization, you know, it's about 40 gigawatt days per ton of heavy metal. I think the figure is climbing up to about maybe about 60 or 50 or 60 gigawatt days per ton of heavy metal. And if you say, you know, if you have a fast reactor, that burn-up could go up to about 100 gigawatt gigawatt days per ton of heavy metal. But of course, I have to say that with a caveat, which is, you know, if you have a sodium fast reactor burning your fuel, getting that very, very high rate of utilization, you would need other things such as reprocessing facilities to make plutonium, high plutonium in terms of ratio, MOX fuel, and that in itself creates a waste stream. So, yeah.
All right, well, thanks very much, Mark. Thanks. It's been a stimulating discussion, and I think we've had some good questions. The slides will go into the ANA website at some point, and I'll send emails to all the attendees or participants with a link to those. And I hope we've got a recording of this, which should be available. But since this is our first webinar, we can't guarantee that process. So thanks, Mark. Thanks for all the attendees for coming, and all the best.
Thank you.
Thanks for that.
Thank you both very much.
Thank you, John and Mark.
Cheers, Ian.
Good. End.